All right, everybody, here we are for Chapter 14 exercises from the back of your book. They start around page 695 if you're following along in the text. The first few questions in the chapter exercises are just asking you to create a frequency table. I'm going to skip that. That's something you should have learned how to do back in chapter 2. So I'm going to go to the ones where we actually use our chi-square or our degrees of freedom or what we've learned this week. So let's look at number 7. For each of the following variables, calculate the degrees of freedom and then identify the critical value of the chi-square for alpha equaling 0.05. So this is one category, and this is going to be a goodness of fit test. And the degrees of freedom in a goodness of fit test are equal to the number of groups minus 1, because we're calculating one chi-square. So for A, degrees of freedom is equal to the number of groups. I've got coffee and tea, that's 2 groups, minus 1 degree of freedom. For B, degrees of freedom equals number of groups, seasons of the year, there's 4 seasons, minus 1 equals 3 degrees of freedom. For C, my degrees of freedom, I have 1, 2, 3, 4, 5 types of movies. Leaves me with 4 degrees of freedom. And lastly for D, I have 1, 2, 3, 4, 5, 6, 7 instruments. Leaves me with 6 degrees of freedom. Okay, now we have to find the value of chi-square for 0.05 with this many degrees of freedom. Let's see, chi-square in your textbook is on page T25. So if I look on page, again, chi-square T25 in your textbook, or you can reference the chi-square table that I printed out or left in Moodle. For 1 degree of freedom at 0.05, it's 3.84. For 3 degrees of freedom, 7.81. For 4 degrees of freedom, 9.49. And for 6 degrees of freedom, 12.59. So that would just involve looking them up. Okay. Question 9 asks us to go back to number 1, calculate the expected frequency and the chi-square statistic for the goodness of fit test for the data in exercise 1 to 3. Assume equal hypothesized proportions. So if we have 2 types, then it's a 50-50 proportion. Question number 1 said the owner of a car dealership interested in assessing young drivers' preferences asks 26 college students to indicate the type of automobile they are more likely to purchase, traditional gasoline-powered or hybrid. Their responses are listed below. So we have a gas option and a hybrid option. So this is the table. It turns out that the gasoline had 10 responses, the hybrid had 16. The total, of course, is 26. This is the frequency that we have observed. The frequency that we're expected, well, when you have 26 observations that are split 50-50, we would expect 13 for each. The next step is to calculate the chi-square. A chi-square statistic, chi squared, for a goodness of fit test is equal to the sum of frequency observed minus frequency expected squared divided by, divided by frequency expected. So I have two rows over here. Actually, I need some more room. All right, so frequency observed minus frequency expected. 10 minus 13 is a negative 3. 16 minus 13 is a positive 3. That is frequency observed minus frequency expected. If I square this, negative 3 squared is 9, and positive 3 squared is 9. I'm going to write it out over here to give me some more room. 9, that's my frequency observed minus my frequency expected squared, divided by frequency expected, which was 13. So I did that for the first one, for the gas, and I have to add these two together, but there's only two of them, and it's the same thing. Nine thirteenths plus 9/13. Pretty sure that means it's 18/13. Gives me a chi-squared of 1.384.38. It's not asking me to test a hypothesis or anything. That's all it's asking us to do. But if we wanted to know whether or not there's a difference in what we have observed versus what we would expect, to take this to the next step, what's our degrees of freedom? Well, we have two groups. We have 1 degree of freedom, and the critical value for 1 degree of freedom at 0.05 is, so critical value of 0.05 chi-squared at 0.05 level is 3.841. So it doesn't appear that there's a strong difference between the two groups. Let's do the third one. The proposed law. A pollster asks a sample of voters to indicate whether they are in favor, undecided, or against a proposed law. Okay, so for the proposed law, you could be in favor, you could be opposed, or excuse me, undecided, or against. When you do the table, you find that 20 people are in favor, 7 people are undecided, 16 people are against. The total was 43. To find the frequency expected, we take our 43 and we divide that by the 3 groups. That equals 14.3333, so 14.3 repeating. This is what we have observed. What we would expect is 14.33. The next step is to take our frequency observed and subtract the frequency expected. So 20 minus 14.33 is 5.67. 7 minus 14.333 is a negative 7.33. And 16 minus 14.33 is a 1.67. The next is to square this. So 5.67 times 5.67. This is a 32.1489. So let's call that 15. We're going to remember we're introducing some rounding error here, but I'm running out of screen space. 7.33 squared is 53.73. 1.67 squared is 2.79. The next step is to take frequency observed minus frequency expected squared, and then go ahead and divide that by frequency expected. So 32.15 divided by 14.33 leaves us with 2.243, so let's call that 24. 53.73 divided by 14.33 leaves us with 3.749, let's call that 75. And 2.79 divided by 14.33 is a 0.194. Okay. So the last step of my chi-square equation remember, frequency observed minus frequency expected squared divided by frequency expected is to do the sigma part and to take the sum of these numbers. So 2.24 plus 3.75 plus 0.19 gives us a chi-square of 6.18. All right, let's look at number 11. Sex in advertising prompts much discussion and media attention, particularly how advertisers blend sex with their brands to gain attention. As part of their study, they asked the following question: are sexual ads more likely to appear in women's or men's magazines? To address this question, they examined the full-page advertisements in a sample of magazines. They found 107 sexual ads divided into men's and women's magazines as follows: 59 sexual ads in women's magazines, 48 in men's magazines. To determine whether sexual ads were more likely to be found in women's or men's magazines, conduct the chi-square goodness of fit test, assuming equal proportions. All right. So state the null and alternative hypotheses. The null hypothesis is that the distribution of observed frequencies fits the expected. So our null hypothesis is that the frequency observed will fit with frequency expected. The alternative hypothesis will be that the frequency observed does not fit with what we expect. Degrees of freedom. equals the number of groups minus 1. So we have 1 degree of freedom. For 1 degree of freedom, the critical value of chi-squared at 0.005 is 3.84. Again, you can look that up in the back of the book, page T25, I believe. There it is, T25, 1 degree of freedom, 3.84. So set alpha, we did that, it's 0.05. Calculate statistic, calculate the chi-square. Okay, so I'm going to go over here and give myself a little bit more room to write. Women, men, frequency observed was 59 women, 48 men, that's 107. The frequency expected is our number, 107, divided by n divided by categories, which was 2. So 107 divided by 2 is 53.5. The next step in the chi-squared, frequency observed minus frequency expected. So 59 minus 53.5 is 5.5. While I have that in my calculator, I'm just going to go ahead and hit the square button, because that's the next step in the equation. And that is 30.25. And then the final step is to take that number and divide it by the frequency expected, which was 53.5. And with that, I get 0.565, so let's call that 57. Okay, going back to males, I have 48 males minus 53.5. Expected is a negative 5.5. We square that, I get 30.25. And of course, if I divide that, I'm going to get 0.57. Sum this, so I was going to take the sum of my two groups. I get 1.14 for a chi-squared. My decision rule said I needed to get out to 3.84 in order to reject the null. I'm at 1.14. So because my chi-squared of 1.14 is less than the critical value of 3.84, therefore we do not reject the null hypothesis. Do not reject. We don't need to calculate the level of significance because it's not significant. Calculate a measure of effect size. We can go ahead and do that. So this is Kramer's phi. Kramer's phi is equal to the square root of our chi-square divided by n times the number of groups minus 1, so our degrees of freedom. Our chi-square was 1.14 divided by n was 107 times 2 minus 1 is 1. So 1.14 divided by 107 is a really small number, 0.0106. I'm going to go ahead and take the square root of that. And my phi is equal to 0.103, so 0.1. That's a small effect. Draw a conclusion from the analysis. Well, even though it appears in the sample that more sexual ads are in women's magazines than men's magazines, the overall difference between the two groups was not statistically significant. So the analysis does not support the hypothesis that sexual ads are more likely to be in a women's magazine versus a men's magazine. Let's look at 13. Historians are interested in the accuracy of eyewitness accounts of traumatic events. One study examined survivors' recall of the sinking of the ship Titanic. The researchers reviewed the transcript of survivors to see whether they testified that the ship was intact or breaking apart during the ship's final plunge. It was in fact breaking apart. I remember that from the movie. List below is the testimony of 20 survivors. So that's our N, and it's 20. And we have two alternatives, intact or apart. Here's our data. It turns out that intact frequency observed is 5 and apart is 15. That's why we have a total of 20. Test the hypothesis that survivors were able to accurately recall the state of the ship at the time of the final plunge. Conduct the chi-square goodness of fit test for these data. Assume that there's an equal likelihood of saying the ship was intact or breaking apart. So if there's an equal likelihood and we have 20 people, we would expect 10 to say that it was intact and 10 to say it was apart. So I'm going to go ahead and write out the steps that I'm going to take. I've got 3. It's good to just go ahead and do it. Okay. So frequency observed, 5 minus 10 is a negative 5. You square negative 5, you get 25. And when you do 25 divided by the frequency expected, which is 10, you get 2.5. 15 minus 10 is a positive 5. Positive 5 squared is 25. Hopefully you've noticed the pattern here when you have two groups. In order to get the chi-square, I have to sum these two. So I have a chi-square of 5.0. Now I had two groups, minus 1 equals 1 degree of freedom. The critical value, remember, for a chi-square, that got messy. Let's do this the right way. Of a chi-squared at 0.05 is 3.84. I just memorized that from our last one. We get a chi-square of 5.0. So where are we? Remember, bucket on the floor. For our chi-square, our critical value was 3.84. We got a 5.0. We are in the reject area. So our chi-square being equal to 5.0 is greater than 3.84. Therefore, we reject the null hypothesis. The last step is to calculate how much of an effect there is. And so if we do Kramer's phi, that is equal to the square root of our chi-squared divided by n times groups minus 1. So that is going to be 5.0 divided by, our n was 20, our groups was 2 minus 1, that's a 1, so 5 divided by 20. 5 divided by 20 is 0.25. Double check the calculator. The square root of 0.25 is 0.5. Okay. Because it's 0.5, I forget what that was, if that was a big effect or not. Let me just check real quick. Yep, that's a large effect. Okay. Number 15. Exercise 2 tested the hypothesis that women are less likely to go to a chain hairstyling store than men. However, rather than assume men and women are equally likely to go to chain hairstyle shops, you learn that the Supercuts chain of hairstyling shops reported that 65% of their customers are men, while only 35% are women. Calculate the chi-square goodness of fit using hypothesized unequal proportions of 0.65 and 0.35. Okay. A student interested in consumer behavior believes women are more concerned about their personal appearance than are men. Consequently, she hypothesizes that women are less likely to go to a chain hairstyling store. Okay, so we got this. Let me put the data up because I cut it off to get it to actually fit. Let's see, I'll have more room. I'll have more room over here. Um, 24 men went and 10 women went for a total of 34. That's what we have observed. Now, frequency expected. Remember, we have unequal expectations. We believe that 65% of our sample is 0.65 times our 34 men. That's 22.1 men are expected to go. And the other 35%, okay, that's what we would expect for women. So let's go ahead and work through our chi-square. The next step is going to be to subtract them. Then after that, we're going to take the square. And then after that, we are going to divide them. So I've got some calculations to make. Grab my calculator. 24 minus 22.1 equals 1.9. Squared is 3.61. And 3.61 divided by the frequency expected, 22.1, this is 0.163. So 1/6. For women, we're going to have a negative 1.9. 10 minus 11.9. Yep, negative 1.9. Square that. We again are going to get a 3.61. Divide that by the frequency expected, which is 11.9 for this one. And we get 0.303. So we're good with that one. We we have to add these together to get our chi-squared, because remember chi-squared is the sum of these for each of the categories. So that's 0.46. So our chi-squared, remember you got to make it a squiggly line, for a chi is 0.46. Now we had two groups, which means we had 1 degree of freedom, which means the chi-square projection area was 3.84, and we got a 0.46. So what does that mean? Well, we got a chi-square that basically says that what we observed is not different from what we had expected. So the number of men and women shopping at a chain or getting their haircut at a change store in this sample is not significantly different from the expected 65-35% split. All right. Question 17. Do people arrested for DWI believe they're problem drinkers? Researchers in one study asked 199 people arrested for DWI, have you ever thought you might have a drinking problem? 19 of the offenders answered yes. And 180 answered no. To test the hypothesis that the people arrested for DWI do not believe they have a drinking problem, conduct a goodness of fit test using a hypothesized proportion of 71.8% yes and 28.2% no, which are based on an expert's opinion as to the percentage of all offenders in DWI programs who in fact do have a drinking problem. Okay, so this is like the last one where we're given the proportion. We're not going to assume that it's a 50-50 split. We're going to use these proportions instead when we calculate our expected frequency. So yes, we have, grab your calculator and type in 199, and the yes percentage is 718, so 0.718. So that should be 142.882. So let's just call that 88. Our no's, we had 199 respondents, and we believe that 28.2% of them should be no's. Sorry, calculator's acting up. Okay, let's try this again. We had 199 times 0.282. That is 56.118. We're going to round that to 56.12. The next step, same with our previous steps. Chi-squared, frequency observed minus the frequency expected, and then we're going to square it, and then we are going to take that number and divide it by frequency expected. Okay, so I like to do this just all in a row in my calculator. We observed 19 minus the 142.88 that we expect gives us a negative 123.88 that we square, which gives us 15346.254. And if we take that number and divide it by the frequency expected, which is 142.88, this number is 107.406. Let's call that 41. Let's go down to our no's. We observed 180 no's minus the 56.12 that we expected is 123.88 squared is 143. Is that again? And divided that number by 56.12, 273.45. Now to get the chi-square, we have to take the sum of these two cells here, 107.41 plus 273.45. Our chi-squared is equal to 380.86. Now, remember, our chi-square what's our critical value? Well, with two groups, that means we have 1 degree of freedom. If we set alpha to 0.05, that is 3.84. We got a 380.86. We are way out here in the rejection zone. So we are going to, because our chi-square is equal to 380.86, which is greater than our critical value of 3.84. Therefore, we can reject the null hypothesis. Now, our null hypothesis was that what we observed is what we would expect. Our alternative hypothesis is that there's a difference between what we observed and what we expect. So our sample is significantly different from the expert's opinion. So if your hypothesis is that people who get DWIs don't think they have a drinking problem, then you would be correct. All right. Now so that was when we had really one category. Right, we had one variable, not category. We had one variable that had multiple categories. Let's look at when we have two variables. Each of the following situations consists of two variables. For each situation, calculate degrees of freedom and determine the critical value at 0.05. So we are going to have something along the lines of, this is going to be a 3 by 2. So to calculate the degrees of freedom, number of rows minus 1 times the number of columns minus 1. So if you have, let's do A, and you have 3 by 2, 3 minus 1 times 2 minus 1, that's a 2 times 1. That is going to equal 2. Don't know why I paused there. All right, B, we have 1, 2, 3, 4. We have a 4 by 1, 2, 3, 4. So 4 minus 1 times 4 minus 1. 3 times 3 is 9. 9 degrees of freedom. For C, we've got a 2 by 1, 2, 3, 4, 2 by 4. Two minus 1 is 1. 4 minus 1 is 3. That's 3 degrees of freedom. And for D, we have 4 grades and 3 residences. 4 minus 1 is 3. 3 minus 1 is 2. That's 6 degrees of freedom. Grabbing our chart and looking them up in the back. For 0.05, 2 degrees of freedom, that is 5.99. 9 degrees of freedom, that's a chi-square of 16.92. 3 degrees of freedom, 7.81. 6 degrees of freedom, 12.59. So that's our critical value. That's when chi-square is equal to 0.05. Okay. In terms of beliefs regarding women's deception in dating situations, Benz et al. Study hypothesized that men, more than women, believe women use deception more often regarding their physical appearance than their financial situation. Below is the contingency table for this analysis. So we have 2 variables and gender and type of deception used. So for each cell we have the frequency observed and we have to calculate the frequency expected. Alright, so let's start. Well, our null hypothesis for these situations are that the 2 variables are independent. So let's call this sex and deception are independent. The alternative says that they're not independent. Alpha we're going to set at 0.05 degrees of freedom. We have 2 rows and 2 columns, which means we have 1 degree of freedom. The chi-square at 0.05 with degrees of freedom equaling 1 is equal to, I think it's still 3.84. Again, just refresh our memories real quick. 1 degree of freedom, 3.84, yep. So if our chi-square is greater than 3.84, we will reject the null hypothesis. Okay. We're given the frequency observed, and we have to calculate the frequency expected. Now remember, in order to do this, we're sort of filling in the cells and we're figuring out how much is expected by, so the frequency expected for row 1, column 1 is equal to the row total times the column total of these numbers. So the row total of 1, 1 is 29 times the column total for column 1, which is also 9, all right, divided by n, which is 90. The frequency expected for row 1, column 2 is the total number of row 1 times column 2 divided by n. Frequency expected for row 2, column 1 this one here, is equal to the row total times the column total divided by n. And the frequency expected for row 2, column 2 is equal to the total of row 2 times the total of column 2 divided by n. So this is just my notation, right? Row 1, column 1, row 1, column 2, row 2, column 1, row 2, column 2. So I'm going to grab my calculator. I'm going to see if I wrote that down correctly. So 29 times 9 is 261 divided by 90 is 2.9. Let's do the next one. Row 1, column 2, 29 times 81 divided by 90, 26.1. So 61 times 9 and then divided by 90 is 6.1. And lastly, 61 times 81 divided by 90, 54.9. Okay. Now, to calculate the chi-square, I have to do frequency observed minus frequency expected. Squared divided by frequency expected. Okay, so let's write this over here, make this look familiar. So this is row 1, column 1. Same steps to get the chi-squared when we have more than one variable, when we've got two variables. So frequency observed for row 1, column 1 was 0. We expected 2.9. The difference between the two is negative 2.9. 2.9 squared is 8.41. And 8.41 divided by the 2.9 that we expected is 2.9. That's spooky. Okay, so I'm just going to go ahead and do these for the rest without the commentary, and hopefully this will make sense to you as I'm doing it. So remember, you'll notice that these columns here are the same, but where it becomes a different number is because for each individual row we have a different frequency expected. So that's why the numbers here are different. And if I did this correctly, 2.9 plus 0.32 plus 1.38 plus 0.15 equals 4.75. That's our chi-square. We would reject the null hypothesis, right? Our 4.75 is greater than 3.84. So this analysis finds that there's a statistically significant relationship between gender and the type of deception used by women, such that a higher percentage of female respondents than male respondents believe that women were more likely to use physical deception than financial deception. The result of this analysis supports the hypothesis that men, more than women, believe women use deception more often about physical appearance than financial situation. Basically, men more than women, think that women lie about their physical appearance. Okay. 23. Remember earlier in class when we discussed personality types of students? Well, what if we go back and do that but add in graduate students? Saying that we reason that grad students would differ from undergrads on personality characteristics that support academic achievement. The following contingency table shows the distribution of these types. Let's go ahead and do a chi-square to see if there is a difference between type of college student and personality type. So what do we have to do? Well, okay, let's take a look at this. We have 4 columns, 2 rows. The degrees of freedom are rows minus 1 times columns minus 1 so 1 times 3 is 3 degrees of freedom. Degrees of freedom gives us a chi-square of 7.81. To reject the null hypothesis, the next step, we have what we have observed, and we have to calculate what we would expect. So let's do row 1, column 1. Let's go ahead and go across. And then I'll do row 2, column 1, row 2, column 2, row 2, column 3, row 2, column 4. Give myself some space. Frequency observed. And I'm going to do this in my calculator for the expected. So frequency observed, I'm just copying here from the table. Now remember, frequency expected, you take the row total and multiply it by the column total and then divide by n. So frequency expected for row 1, column 1, so it's 588 times 339 divided by 735, leaves us with 271.2. So for row 1, column 2, I take row 1's total and I multiply that by column 2's total and then divide by n. 64.8. Row 1's total times column 3's total divided by n. Row 1's total times column 4's total divided by n, 735. Now I'm going to switch down to row 2. So it's going to be row 2's total times the column total. So row 2 is 147 times column 1, 339, divided by the sample size, 735, gives me 67.8. Okay, 147 times 81 divided by 735 gives me 16.2. 229 times 147 divided by 735 and last but not least, row 2's column, or row 2's total times column 4's total divided by the n. Okay, there we go. It takes a little bit of time, but you can do it. So now that I have my frequency observed, my frequency expected, I have to take the difference. Then I have to square it. Then I have to divide by frequency expected. So again, I'm just going to do this row by row and write in the numbers, and I might just actually skip the first two numbers and just write the last one that I'm going to add up. So 251 minus 271.2, I take that number and I hit the square button, and then I divide that by the frequency expected for that row, and I get 1.550. So the next one is 65 minus 64.8 squared, and then divided by 64.8. That's a really, really small number. That's 0.000. I'm just going to leave that like that. Okay, 194 minus 183.2 squared, and then divided by 183.2 is a 0.636. Let's call that 64. 78 minus 68.8 equals 9.2. Squared is 84.64 divided by 68.8 leaves me with 1.230. Okay, so I've done that for each of my numbers. I'm going to sum it so that I can get the chi-squared. 1.5 plus 0 plus 0.64 plus 1.23 plus 6.02 plus 0 plus 2.55 plus 4.92, and I get a chi-squared value of an error. Oh, come on. Too many fingers here. 1.5. Sorry. My calculator really doesn't like me. Okay, let me do this really quickly again. I got 16.86. Whew. Finally. Is 16.86 greater than 7.81? Yes. We can reject the null hypothesis. What does that functionally mean? Well, the distribution of the 4 lifestyle types differs depending upon whether you're a college student or a graduate student. So this analysis supports the hypothesis that the distribution is affected by college student type. All right, let's do another one. Do children think bedtime stories are real? One study examined whether children's beliefs regarding the reality of people or events and stories depended upon the type of book. In the study, 3-year-old children were read 4 books that were one of 3 types: realistic, fantastical, or religious. After listening to each book, the children indicated whether they believed the people or events could exist or happen in real life. The children can be grouped into one of 2 categories based upon the number of books with people or events they believed could exist in real life. None of the books versus one or more of the books. Imagine the researchers hypothesized that children were more likely to believe realistic books were real than fantastical or religious books. Listed below are the data from the study. I skipped that part. We end up with a table that looks like this. So this is how many they believed were correct. I gotta admit, I don't really understand what they're trying to get at here, but it doesn't matter, because I can go ahead and compute a chi-square. I don't really have to understand it as long as I apply the math rules. I've got to do the totals of my rows and columns. My overall total was, I don't remember, 50. Okay. So what's our null hypothesis? Our null hypothesis says that the variables are independent, so there's no relationship between the 2 variables. Null hypothesis, or excuse me, alternative hypothesis says that the 2 variables are not independent, so that there is a relationship. Frequency observed, sorry, before we get to that, let's have some agreement on the degrees of freedom, the number of rows, 2 rows, number of columns, -1, 1 times 2, we're going to have 2 degrees of freedom. 2 degrees of freedom at the alpha of 0.05. The chi-square is 5.99. So we need to have a chi-square greater than 5.99 in order to reject the null hypothesis. Okay. Now, how to do this? Well, again, I need to set this up in a different way. I'm going to erase this to give myself some room, which was kind of stupid of me. I should just make this smaller. Let's make it really tiny. So I have 2 rows, 3 columns. Row 1, column 1, row 1, column 2, row 1, column 3. Remember, important thing is to do this the same way every time. Same way every time. The frequency expected for a number is the total of the row times the column divided by the n, divided by 50. So I'm going to use this to go through and look at my row 1, column 1, 34 times 17 divided by 50 leads with an expected of 11.56. Row 1, 34 times column 2, 21 divided by 50, 14.28. Row 1 times column 3, total, divide that by 50, 8.16. Row 2, so now I'm down here at the 16, and then I'm going to go this one, and this one. 16 times 17 divided by 50. 16 times column 2, which is 21, divided by 50. And last but not least, row 2 is 16 times total for column 3 is 12. Divide that by 50. Okay. So I have my frequency expected. The next is just the subtraction. So 9 minus 11.56 squared, and then divided by the frequency expected for that value. 5669, so 5.7. All right, so I'm just going to go through and do these and then write the last column since that's the one I really need. So here's my 6 values, and I'm going to add them all up to get to the chi-squared. And I got 2.69. So that's my chi-squared for this. Now, is 2.69 greater than 5.99? No. So we cannot reject the null hypothesis. Do not reject the null. Again, I still don't really understand this one, but in a sample of 50 3-year-old children, a chi-squared test of independence indicates a non-significant relationship between the type of book read to them and the number of books they believed contained people or events that could exist or happen in real life. The results of this analysis does not support the research hypothesis that children are more likely to believe that realistic books are real than fantastical or religious books are real. So basically, children know they're being read a story. Ta-da. Okay, that's it for this section of chi-squared. The biggest thing to remember is that we have 2 types of chi-squares. The first type of chi-square is known as a goodness of fit. And this is when we have one variable and we want to see if it meets expectations and how it is distributed. So essentially, if you're doing something that is male and female, does it fit the 50% split? Or if you have some research, you can actually change this number and use that when you calculate the frequency expected. Chi-square, frequency observed minus frequency expected, squared divided by frequency expected, and you take the sum for all of your rows and columns, or all your rows, I guess, in this instance. For another version of the chi-square is when we have a contingency table, and that contingency table has us set up so that you have a difference between 2 groups. This is your independent variable. Your dependent variable is the outcome. And in that case, you have to, the chi-square is the same formula, but it gets a little bit more complicated. Your degrees of freedom is the number of rows minus 1 times the number of columns minus 1. And the frequency expected, instead of just taking the total n and dividing it by the number of groups like you would for the goodness of fit test, for the independence, the test of independence, the frequency expected is the row total times the column total divided by n. So that's where, when you're thinking about your cells, this is row 1, column 1, row 1, column 2, row 1, column 3. Okay, that's the chi-square. Like I said, it's not difficult. Really what we're doing is looking at the difference between frequency observed and frequency expected. That's the whole focus of this, and we can use it if we're trying to compare two groups when we have categorical dependent variables. And that's it.